Hi there. So the next property of seawater that we are going to investigate is the alkalinity. And to do that, we'll be doing a titration to determine the total amount of basic substances in the seawater. And typical to any titration reaction, we need to know the concentration of the titrant in order to solve for the unknown, which is the analyte concentration. So first off, we need to do a standardization in order to know that concentration of titrant. So the second part of this experiment is the alkalinity titration, but the first part is this coulometric titration, where we're just standardizing the titrant. So I've separated these into two videos to keep them separate. The coulometric titration is simply for standardizing, not for determining alkalinity. Okay, so the goal here is to standardize of the titrant. In this case, our titrant is hydrochloric acid. Okay, so maybe you've done this before in a past class where you've standardized your HCl by reacting it with hydroxide. So you take that H plus from the acid and neutralize it, forming water. And maybe you've done that before where you took your HCl and you standardized it with sodium hydroxide, NaOH, and you neutralized it and you witnessed the endpoint using phenolphthalein indicator, for example. So we could do that, but we're going to try something a little bit more sophisticated, being this coulometric method. So H plus is the analyte, OH minus is the titrant. Instead of using NaOH, what we're going to do is generate our OH minus by reducing water. Okay, generating. Okay. Now, if you supply, or if you just have water sitting, it's not going to generate enough OH minus all on its own. Okay, so this is a non-spontaneous reaction, which means that we have to supply some electrons to the water in order to cause this reduction reaction to occur. Okay, and when you supply electrons to this kind of reaction, it's called an electrolytic cell. Okay, and we're going to supply electrons at a constant current. So the first step in the procedure of this reaction is to build this constant current circuit yourself, which is a skill that's important for analytical chemistry. I myself in my lab occasionally have to work with electronics. It's important. No instrument can run without electricity. So let's start off by thinking, if you plug something into the wall outlets output AC current. It's oscillating back and forth. It pushes some current and then goes back, goes like this. But if we want to supply a constant current, we can't have this pushing force. Instead of using that alternating current, we need to use direct current. So the very first step of our circuit is going to have an AC to DC converter. So we're going to be taking the 9 volts of AC that comes out of the wall and converting it to DC, direct current. Okay, and so that is signified by this first symbol. It's like a battery. And coming out of one side of that battery, the first component we'll hit is this diode. A diode is a component that only lets current run in one direction. Okay, so current cannot flow backwards through this current back to the source. Okay. Next up, we're going to encounter a capacitor. And a capacitor is used to store charge. Okay, now the most important part of this circuit is coming up now. This is called a voltage regulator. And what happens is we have some voltage coming in. That's that 9 volts. We haven't changed anything yet. The 9 volts comes in, and then it comes out the other side. And it's going to pass through a resistor, which is a squiggly line. Resistor. And this is a voltage regulator. Okay, and then what that resistor does is blocks current. It tries to inhibit current from going through. So you have that 9 volts. The electrons are trying to flow through, but it hits this resistor, which stops it. And so your voltage is going to decrease, or your current is going to decrease. And what we do is loop it back around, right back into the same voltage regulator, and that's an adjusted voltage now. Now that it's gone through that resistor, now we have a different voltage amount. Okay, and that adjusted voltage is going to go right back out again and through the resistor again, and so forth. Now, the voltage regulator that we're using in this experiment is designed specifically. Okay. It is programmed to do one thing. It takes whatever voltage comes in and it spits out one voltage going out. And that exact voltage that it's always going to spit out is 1.25 volts. Okay, so that means no matter what is happening with the wall current, say for example, someone goes and presses the elevator button down the hall, and now the elevator is drawing a ton of current in order to move the elevator up and down. And that means the current that you're getting out of the wall suddenly decreases. It wouldn't matter because we have this voltage regulator here to make sure that no matter what the input voltage is, if it decreased because someone pressed the elevator button, that it's still going to spit out 1.25 volts. Okay, and that capacitor helps since it's storing some charge. In case you're running low from the wall, the capacitor can help back it up. Okay, so one thing to think about too is, okay, if we are constantly spitting out 1.25 volts, and if our resistor has a resistance of 66 ohms, in this case we're using 2 resistors back to back, each with 33 ohms, and resistors in series add together, that means we can determine what the current we are outputting here is. Okay, by V equals IR, we can calculate that. Solve for current I, V divided by R, 1.25 volts divided by 66 ohms, and we should get a roughly 19 milliamps. Okay, amps are the unit for current. Cool, so that's the current that's coming out right here. Okay, lowercase I, capital I, interchangeable. Okay. So let me add, along this circuit, we're gonna just add a voltmeter or amp meter, because we wanna make sure that we can measure the current coming through and see that it is roughly that 19 milliamps that we expect to read. Okay, on the other end of the circuit, We need to add a switch. Okay, the switch is going to act just like a stopcock on a burette in this experiment. Oops. You'll close it, you'll open the switch, meaning breaking the circuit, which means no current can run through in order to stop the flow of electrons so your titration is not going forward. And then you close the switch, make sure that current is flowing through to continue your titration. Okay. I'm gonna move it on to the next page here. Now, these two ends of our circuit are gonna lead to two electrodes, which we will have in a beaker. Okay, solution. Those electrodes will be submerged. This side is the cathode, where reduction happens, and this side is the anode, where oxidation happens. And our solution is going to have our analyte in it, the HCl, which of course dissociates into H plus and Cl minus. Okay, and so the reactions that are happening here, I said earlier that we are providing electrons to our solution in order to reduce water and generate the OH minus, which will then titrate our acid. So let's draw out those reactions. At the cathode, we're going to reduce our water. That water in solution there, this is also H2O. And by adding electrons via our constant current circuit, I think it's 2 electrons, we will reduce our water into H2 gas and OH minus. Okay, so there is our titrant. Okay, at the anode, we'll be oxidizing water. This is just kind of a side reaction. We need to be able to neutralize our electrons, so the water will be oxidized. Okay. Awesome. So this is what's happening in a very basic sense, and this OH minus is then reacting with our analyte, the titrant, the HCl that will be used in a titrant in part 2. Okay, some procedural notes, because this gets kind of complicated here. Oh, hello. Okay. First thing I'd like to point out is that our analyte is this HCl, but we are adding it to an electrolyte solution of NaCl. Sorry. Analyte HCl is added to a solution of NaCl. Okay, so that means there's also some Na plus and some more Cl minuses floating around in there. Why do we do that at all? Why don't we just stick our electrodes straight into our HCl that we're trying to analyze? It's just a matter of charge transportation. Having those ions in solution helps transfer charges and move electrons throughout the solution. Okay, another thing is that we need to store the anode in a compartment. We can't just stick it directly into our analyte solution. Why do we need to put the anode in a separate compartment? Well, as you can see in the reaction above of what happens at the anode, and this is just one reaction that happens at the anode, there are a couple side reactions too, you'll notice that it generates more H+. And that would be a problem. If you had your anode directly in the solution, you would be adding more H+ to the analyte solution, but we only want to know how much is in the original solution. We don't want to be adding more and disturbing our results. Okay, so that's why we need to separate it off, make sure that any H+ that's generated from the anode stays separate. Another important note in the procedure is that, okay, now we have our anode in a separate compartment, and you need to fill that compartment with some electrolyte solution too. Okay, you just need that there again for charge transportation. You need something for your charges to flow through. But that electrolyte needs to be emptied out and refilled between each trial. Why? Why might we need to do that? Well, let's look at some side reactions that happen. Apart from generating H+, we're also generating another product that we don't want to have around. So notice how we have these chloride ions in solution, and those can also be oxidized. Cl- can form Cl2, chlorine gas. And that chlorine gas can react with the water, and it'll form bleach. Not to mention some more H+ again. Bleach. So as you do this reaction, you might notice you start to smell some bleach, and that's from that anode compartment electrolyte. But again, why do we need to empty it out and refill it? Well, this bleach can actually interact with our indicator and make it useless. And we do need an indicator, which gives me the perfect segue into the fact that we're using an indicator. Okay, like I say, you maybe done this neutralization before using phenolphthalein. This time we're providing electrons, and how are we going to know when to stop providing electrons? By using an indicator to spot the endpoint. And this time we're going to be using bromothymol. And let me just draw out the color scheme for this one. So in basic solution, bromothymol is blue. In acidic solution, bromothymol is yellow. Okay, and when you mix blue and yellow together in the middle, that gives you green. Okay, and this green color in this indicator happens from roughly pH of 6 to pH of 7.6. Okay, so let's think about what that means. If you have your your analyte, the HCl, in your beaker, what color would you expect the solution to be if it has the indicator in it? So this is at the beginning of your titration. It should be yellow, right? Because the HCl is acidic. And then what should the endpoint be? As you're adding electrons, you're generating OH minus, and that's neutralizing your acid. And so your endpoint should be green, right? This between 6 and 7.6 is around neutral. Okay, so the endpoint green. So that's what you'll be doing. You'll be providing current until you notice your solution is green, and you'll stop it, and you're going to time how long that takes. And we'll get into that math in just a second. Just one other thing I do want to add about this to think about. What if you just have your electrolyte solution in your procedure, your very first trial, you made your salt, and you add your indicator, and you have not added your analyte yet, your 1 gram of HCl. What color do you expect that to be? Ideally, it would be green, neutral, right? You haven't added any acid yet. It's just DI water and sodium chloride, should be neutral. But sometimes the DI water we get from the tap is a little bit acidic, so you might observe that it's yellow before you even begin your first titration. I want you guys to think about what kind of error that might cause on that first trial. If there's already acid in there, then when you do your first trial, that one should take longer to neutralize, right? That's going to be a systematic error on that first trial caused by the acid that's already in the solution. Okay. If that's the case, you might want to address that in your analysis. One other solution, a proactive solution, might be to neutralize before you even do your first trial. And that would be a blank titration. Okay. So overall goal of this part is to calculate the concentration of HCl. So let's go through that. Calculate. Okay, so what we want at the very end here is concentration in moles of HCl per kilogram of solution. Okay, what do we know from the beginning? We do this titration, and the two things we measure are time and the current that we apply. Okay, so if we start with how long our titration took, time in seconds, and then we also know the current. So if we multiply by the current I, notice that current is measured in amps, which is the same as coulombs per second. Okay, so this way, by multiplying by current, we can cancel out those seconds. And now we have the coulombs that we've applied to our reaction. Okay, and then look, our goal here, we're trying to get moles of HCl. That means we're going to have to work backwards through our titrations. Let me scroll up here. Okay. We're trying to get moles of H+, which means we need to know the stoichiometric ratio to OH-, which means we need to know the stoichiometric ratio from OH- to the number of electrons. So that's where we're going here. Since we're applying a constant current, we can convert from time into the moles of electrons. So far, what we've done is take time and multiply it by current. The next thing, to convert from coulombs into moles of electrons, we have what's called the Faraday constant, okay, F, and that converts, like I said, from coulombs into moles of electrons. And now we can go ahead and work in those stoichiometric ratios. Looking at those reactions from previous, 1 mole of electrons generates 1 mole of OH-. and 1 mole of hydroxide neutralizes 1 mole of H+. Okay, so we have our numerator figured out already. Now we just need to divide by the mass of the solution, and that will give us our answer. If you want that in a more concise form, this entire analysis can be summarized as current times time divided by Faraday's constant and the mass. Okay, don't forget error propagation. As per usual, think about some sources of error: systematic, random, percent error, precision. You know the routine. Okay, have fun.